Hello again. Right, next video. Following on from the hydrolysis reaction with drop-wise ammonia, I'm now going to do the one for sodium carbonate. Now, all of these do seem like a lot of equations, and there are simple ones, and you may think, what's the point in knowing all of this? Well, firstly, it gives you an understanding of the background, but it's also, this is the first visualization that you've seen of equations involving transition metal complexes. And so just watching the equations being formed is actually a useful exercise. So as I've said previously, copying all of these equations down isn't important. The very first equation of the reaction of water with the aqueous metal ion, you need to know about that. All the subsequent ones, you can write them down if you want, you can practice them. They're not essential that you know how to produce them, but you need to know what's going on. Now, the last one that I'll do about the background to the hydrolysis reactions involves sodium carbonate. Now, sodium carbonate is Na2CO3, not NaCO3. It's CO3 2-. But just like in NaOH, we don't normally show, well, to be honest, I've never bothered writing the Na plus ion. So when we're doing equations in transition metals with that, we only show the CO3 2-. Now, I've stuck to Fe2 plus so far, but I'm going to need to use a 3+ ion. It's only 3+ ions that react in this manner. So I'll use Fe3+. Now, an overall equation for FeH2O6 3+ reacting with CO3 2- with carbonate. Now you can see that goes on to form FeH2O3 OH3. It forms a precipitate. For a 3+ metal ion to be a precipitate, it's got to lose 3 H+. So it goes from the 3+ down to neutral. So that means we have 3 water ligands and 3 OH- ligands. And then because of that, we also form H2O, let me get rid of that there, plus H2O and also CO2. If you can remember back to GCSE chemistry, a carbonate reacts with an acid. Now 3+ metal ions are much more acidic than 2+ metal ions. So that complex is acidic. So an acid plus a carbonate gives a salt plus water plus carbon dioxide. This is the one extra observation you see. Now you've got to balance that, and it's not that easy. Now it's not redox. We can't just throw electrons in there, because you can tell it's not redox because the Fe is a 3+ over there. That's still Fe3+. That's also Fe3+. No elements have changed their oxidation state throughout that. So the problem that we've got is this side over here is +3 and 2-. So that's +1 at the moment. This side is 0 charge. As I've said, we can't add electrons to balance these charges out because it's not redox. So what we've got to do is we've got to use the charges to balance these out, and that's the easiest way of actually going about this. If this side is 0, we've got to make this side 0. We can't make that side over there anything other than 0. It will always remain it. So we've got a 3 and a 2. If you remember back to constructing formulae, aluminium oxide Al2O3, if you've got a 3 and a 2, you want a 2 and a 3. 2 of that and 3 of that. That's 6+ now, that's 6-. That side is 0 overall. Now the knock-on effect of that is that we've got 2 Fe's there, so we want 2 of that complex. We've got 3 carbons, so we want 3 CO2s, and then the water mirrors it. You just remember that. Whatever carbon dioxide you get the same water. So remember, that's a squiggle out, sorry. That is still a hydrolysis reaction. So what that means is that actually, because it's hydrolysis, that carbonate isn't actually reacting with the transition metal complex. It's reacting with the H3O plus that's present in the solution with that. So I'll just quickly go through this, give you an idea of what's going on. It's a bit more complex, this one is. Mainly because we've got a 3+ ion, so we've got 3 steps of equilibria to go through. So the natural equilibrium that's occurring, FeH2O6 3+ plus a water molecule in equilibrium will go on to form FeH2O5 OH. Now this goes down to 2+ plus H3O plus. But then we add the carbonate. Carbonate is a weak base like ammonia. So CO3 2- plus H3O plus. Now what that forms is water and carbon dioxide. But that blatantly doesn't balance. So we're going to need, that side is 0 charge overall. We have to make this side 0 charge overall. 2-, that's now 2+ because we've got 2 of those H3O plus ions. Therefore we want 3 of those. So that is the first step. Second step, made more H3O plus, carbonate comes in, reacts with H3O plus in the same manner as the previous one to give 3 H2O plus CO2. And then this will go one more step to go down to the precipitate. Oh, sorry, that should be a 4. And then by the addition of more CO3 2-, more carbonate, that causes this equilibrium to shift fully to the right. And then ion 3 will not go any further. It will not allow the removal of any more H pluses or protons than that. Okay, now we've got to cancel all that down. But the only problem with this one is it's a bit more complicated. Yes, we've got the complex appears on the right there and on the left there, so we can cancel that down. That one appears on the right there and the left there, so we can cancel that down. But this is where your understanding of combining half equations with unequal numbers of electrons on the right and the left come in. 1 H3O plus there, 2 there. So what we have to do to this is multiply all of that one by 2. So then we've got 2 H3O plus, which will cancel out those 2. That one by 2 to cancel those H3O pluses, so you can't see that, with those. And then that one by 2. So let's start cancelling these down. So 2 of the 5 and 1 complex cancels out 2 of the 5 and 1 complex. 2 of the 4 and 2 complex cancels out 2 of the 4 and 2 complex. So we've wiped out all the complexes aside from the start and the finish. Then we've got on the left here, this is where cancelling it out in this method is going to be a bit more complicated. We've got essentially 2 H2Os there, 2 H2Os there when we've multiplied there, 2 H2Os there. That in total makes 6. That will cancel out 6 waters on the right. So if I wipe all of those, and that will cancel out 6 waters on the right, but leave me with that. H3O pluses. 2 H3O pluses there, cancels out 2 H3O pluses there, 2 there, cancels there, 2 there, cancels out there. So what we're left with now in that mayhem is we've got 2 lots of our starting Fe complex. We've got 1, 2, 3 carbonate ions. We've got one of our finishing precipitate complexes. So we've got 2 of them. We've then also got, we've cancelled out all of the waters except for these here, 3 H2O, and we've also got 3 CO2s. So you can see that first method, learn the starting complex, learn the finishing complex, know the formula of the carbonate and that you produce these, and then balance it according to charges. But that is what's going on. It's just another example of how carbonate, like dropwise ammonia and dropwise sodium hydroxide, all behave via a hydrolysis or an acid-base reaction. Because in each case, the metal complex was the acid and the OH minus NH3 or CO32 minus was the base. Okay, so hopefully that's given you a bit more idea and hopefully resolved some things, but seeing more of the construction of transition metal complex equations is actually a benefit. Okay, well I will be doing another video showing how to compose equations for moving from one complex to another, and also substitution reactions as well. That's the one type left. Thanks a lot.